Okay, previously we have discussed on the rectifier how the AC is converted to the DC signal. So next, the DC signal needs to be smoothened out or using the filter circuit. So this is using the filter circuit. Why is filter? Filter is a circuit that reduces the variation in rectifier voltage. So the rectifier voltage, although the voltage has only one current direction, but the value for the voltage vary a lot. So filter reduce that variation. So the filter is simply a capacitor connected to the rectifier output to the ground. A small amount of fluctuation in the filter output voltage is called ripple. Ripple factor is an indication of the effectiveness of the filter. So the third and the fourth statements means that after the filtering process, we cannot get a very fixed or very clean horizontal voltage line, but there will be some fluctuation. So this fluctuation is called ripple. So the ripple factor actually indicate the effectiveness of the filter. If the ripple factor is 0, means that there is no fluctuation. So this is the ideal condition. Okay, this is power supply filtering. So without the filter, we have this is full wave rectifier, become like this. So the current vary from 0 to the peak voltage. If the output of full wave rectifier is connected to the filter, you can see the output voltage will vary from the peak until a voltage point which is below a little bit below than the peak voltage. So the variation in terms of the output voltage is very low. So this is how the slide show how the capacitor can smooth out the output voltage. So we know that the capacitor can act as a DC source through the charging and through the discharging. So it's charging and discharge. So the capacitor here at positive cycle. So this is this positive cycle when the input is at the positive cycle, and then the input is larger than the diode knee voltage or barrier potential. So there will be a current flow. When there will be a current flow, so what happened? At first, there is no charge in the capacitor, but through the current flow, the capacitor will be charged. There will be a charging process. So the capacitor at peak voltage, the capacitor will be charged until the voltage equal to the V peak. Okay, equal to the V peak. So this is a charging process. Okay, so here the output will be equal to this one, to be this green waveform. So when V in begin to decrease below its peak value, the capacitor retain its charge. Okay, so and here the input voltage decrease from the peak value. So at this point, the capacitor is already hold a voltage. So it already hold a voltage. So it will retain the charge. So at the moment where the diode is turned off, the capacitor will act some sort of like DC source. So it will provide a voltage to the load. So here the capacitor will discharge the whole charge. So it will provide a current to the load. Okay. During the remaining part of the cycle, the capacitor can discharge only through RL at the rate determined by the time constant. So you can see here the voltage of the RL. so decrease, so the RL will not be at VC or at the peak, because the charge inside the capacitor will become lesser over the time through the discharging process. So that's why the voltage decrease. So the rate of the decrease or the rate of discharge is determined by the time constant, which normally long compared to the period of the input. So at this point, discharge until the voltage come here. So at this time, the input will be at the positive cycle again and exceed the value of the capacitor voltage. And when the input is higher than the capacitor voltage, the capacitor will be in charging condition. Okay, so diode will be again become forward bias input exceed the capacitor voltage by VD. Okay, so this is the comparison between the filtering of half wave and full wave. Okay, so in this slide, where is the part of the charging occur? Charging occur at this part, and discharging occur at this part. So this is charging, and this one is discharging of the capacitor. So in the half wave, the discharging period is quite long, so the ripple, this is what we call a ripple. Okay, this is ripple. The ripple is quite big or quite large. Okay, but in case of the full wave rectifier, the discharging will take place at a shorter time. Okay. So here the B is the filtering, the output voltage after the filtering with a smaller ripple. So the smaller ripple means that we have the better or effective filtering. Okay, the variation in the capacitor voltage due to the charging and discharging is called the ripple voltage. Generally, ripple is undesirable. The smaller ripple, the better the filtering action. Okay, sorry. This is the actual the slide that show the comparison between half and full wave. So at the full wave, the discharging part is shorter compared to the half wave. So the output voltage will not be as lower as the case for the half wave, because the discharging time is shorter. Okay, so the ripple will be much smaller in the full wave. That's why we use the full wave rectifier. Okay, so next part, I will introduce the ripple factor R. What is ripple factor? Is the ratio of RMS value of AC component. So in this context, AC component, this is a ripple. Okay. The ratio RMS value over average value. So ripple factor is VRMS over VDC. So VDC, how we define the VDC? VDC is VDC is actually the V peak. VDC is equal the V peak rectifier minus V ripple peak to peak, half of V ripple peak to peak. So this is the definition of VDC. So V ripple peak to peak is defined by the difference between the peak, the highest point, and the lowest point of the ripple. So this is, let's say I put this one, and this is 2. So V ripple is 1 minus 2. Okay. So how we can calculate the V ripple factor is by using this general equation. Okay, but when you use this general equation, actually you can get, or you can arrive to this equation. Okay, this table summarizes the important equation for the waveform related to the filtering circuit. So, for the waveform after the filtering, the general loop or general pattern, okay, how to draw the output after the filtering is, let's say this is V and this is T. First, you need to have the this is the full wave. So the base, this is the, you put a dash line, this is for your guide line, this is for full wave after the rectification. And then next, you draw this line. So this is the output, the ripple output. Okay. So the peak here, the peak, the V peak of the ripple will be equal to the V peak after the rectifier. Okay. So and then you need to calculate this one is VR peak to peak, the peak to peak of the ripple voltage, by using this equation. Okay. Using this equation, you can get the VR peak to peak. And then if you need to calculate the VRMS, you can calculate using this equation. And then VDC is using this equation. And lastly, the ripple factors is given in this equation. Okay, let's do an example of a rectifier circuit and the filter circuit. Okay, the task is we want to draw a waveform at the secondary terminal of the transformer. So where is the secondary? At this point. So you put a V secondary, and at the output. So this is V out. Okay, for the V secondary, let's assume the input is sine wave. Okay, when you want to draw the input of the sine wave, the first thing that you need to determine is the peak voltage. Okay, this is for the y-axis, for the voltage axis. The provided information is VRMS, so you need to convert. The peak of the primary is equal to square root 2 times VRMS, 115. So this is equal to 162.6 volt. Okay. So and then next for V peak for V secondary. V peak for V secondary. Okay. So V peak for V secondary, you need to consider the turn ratio. So this is N secondary over N primary, 10, and then times 162.6 volt. So this is equal 16.26 volt. So we know the V peak secondary. Okay. So the important parameter for the voltage axis is already known. So next for the in order to draw the graph, For the x-axis is time, so you need to know the period. So the period is 1/60. So this is 16.7 millisecond. So the first answer, this is T millisecond, this is V secondary voltage. The rough sketch will be something like this, 16.7, and this is 16.26 minus 16.26. So this is the answer for number 1. Okay, for answer for number 1. Okay. For the answer for number 2, okay, number 2, there are rectification process and filtering process. So let's consider the output after the after rectification process. Let's say I put a V-peak rectifier. Okay, V-peak rectifier is equal to V-peak secondary minus 1.4, because every current or every cycle of the input, the current flow will pass through 2 diodes, so it will be 1.4. So this is equal to 16.26 minus 1.4 equal to 14.86. Okay, at the moment this one is V rectifier. So V rectifier. Okay. So next is filtering process. So for the V peak of filtering should be equal to the V peak rectifier, which is 14.86 volt. Okay. However, in order to draw the output after the filtering process, you need to know the peak to peak of the ripple voltage. Okay, because the waveform of the output after the filtering process will be look like this. Okay, so first you need to have you need to draw. This is the full wave rectifier. Okay, so the actual line will be okay. So this is the peak here. The peak here is equal to the peak for the rectifier, 14.86. This is the B filter voltage. This is T. So this is 16.7. Okay, so what is the value for this one? So for the value for this one, you need to calculate the V ripple peak to peak. So V ripple peak to peak is given by V ripple peak over 2 frequency and then RLC. So this is 14.86 over 2 times 60 times 2.2 kilo ohm times 50 microfarad, which is equal to 1.126 volt. So here the value is 1. So let's say I put this V1 is equal to 14.89 minus 1.126. So this is equal to 14.89 minus 1.126, 13.73. So this is 13.73. Okay, now you get the answer for number 2. Okay, if you need to get the DC voltage after defiltering, the DC voltage is defined by V peak, VR peak, the peak for the ripple, minus 1 over 2 VR peak to peak. So this is 14.86 minus 1.126 divided by 2. So you should get 14.3 volt. So this is a DC voltage. Okay.